Okay, so this video looks at the dot product. It briefly introduces the dot product and then shows you some uses of it through some examples. Hopefully the meaning of it will become more obvious when you see the examples. So if you imagine you have two vectors, A and B, and they're separated by an angle which we'll call theta because everyone does, then you can take vector A, B, dot in the middle, the dot product, that's the same as the magnitude of A times by the magnitude of B times by the cosine of the angle between them. So the result of a dot product produces a scalar value. You can see it's all scalar on the right hand side of that equation. The units of the dot product will be the units of vector A and vector B multiplied together. So for instance, if vector A was a force and vector B was a direction, then you'd have newtons and meters, so the units of the dot product will be newton meters, which gives you a hint on moments later on. We already know just some simple definitions that you'll find in your in lecture 2. I crossed with J, I dot J, not I cross, I dot J equals 0, and you know that because cos theta, well they're at 90 degrees to each other, and cos 90 is 0. Similarly, you know that I the dot product of that will be 1 because the magnitude of a unit vector is 1. How would you do that? Well, all you do is you take, if you had AXI plus AYJ plus AZK, and you're making a dot product with, let me clear a bit of space here, we're making a dot product with BXI plus BYJ plus BZK. So this is just like in the lecture notes. If you cross them together, you'd have AX times BX plus AY, times BY plus AZ times BZ. I don't know if I've got times in there and not in the other two. But you can see there's no i's, j's or k's because it's a scalar result. So we can use that for several things. We can also rearrange the equation to say to find theta. So it's the inverse cosine of A dot B over AB. We can also, if you look at slide 58 in lecture 2, you can see that you've got a vector here, vector A, and you might have a unit vector down here defining a line, and that might be the line that's horizontal, or you could be defining a perpendicular line to that. If you define unit vector A as I've shown here, and you already have a Cartesian vector for vector A, if you find the dot product of those, you can work out the magnitude of vector A that's acting along the horizontal line. So how much of vector A is acting in that direction. And we can also use it to work out more complicated examples. To see an example of that, if you turn to slide 60 on your on lecture 2, I'll briefly draw it out, but you may want to look at the actual diagram for clarity. Then I'll talk you through it. So as I say, not the clearest diagram in the world, but you've got a force acting with a Cartesian vector of minus 6i plus 9j plus 3k, and it's being held at a point which in your diagram is a hook at A, and there's another line indicated with an angle of theta between them, AO, and you're asked how much of the force that's pulling on the chord with the vector given is acting along the line AO. So how much of the force defined is acting along AO, and you're also given some dimensions. So the first thing you're going to want to do is define the direction AO, and you do that with a unit vector. So RA to O is a vector. Well, maybe easier to look at your diagram, but you're going to be going -1 in the I direction. You're going to be going +2 in the J direction. So in the I direction we're going from A, which is here, we're going backwards 1. In the I direction, from A to O, we're going to go +2. And in the K direction, we're going to go down -2. So -2K. And then you're going to work out how far it is from A to O. So from A to O, it's going to be 1 squared plus 2 squared plus 2 squared, all square rooted, which is 3 meters. You've already given your force as a Cartesian vector. You can work out the magnitude of that force. So you can say the magnitude of the force that's been defined is going to be 6 squared plus 9 squared plus 3 squared, all square rooted, which is going to be 11.22, and this unit is kilonewtons because that's what it's given in the question. And you're going to want to find the dot product. So the dot product, if you're using F and RAO, is going to be -6 times -1. So -6 from the first part of the Cartesian vector for the force, -1 from the position vector for AO, plus 9 times 2, your J components, plus 3 times -2. That works out to be 18 kilonewton meters. So 18 kilonewton meters is the result of the first bit. We can then substitute into that rearranged equation because we know everything we need to find the angle. So the dot product bit was 18 kilonewton meters, the magnitude of the force was 11.22, and the distance was 3 meters. That will work out as an angle of 57.67 degrees. We can work out our unit vector, AO, using our position vector and the magnitude of the position. So -1/3 I plus 2/3 J minus 2/3 K. I can then say, well, the force acting along line AO is going to be the dot product of the force and the unit vector AO. So it's going to be -6 times -1/3 plus 9 times 2/3 plus 3 times -2/3, and that's going to equal 6 kilonewtons. The alternative method of doing that, you could say FAO equals F cos theta, which is 11.22 cos 57.67, which equals 6 kilonewtons. So at this point here, there are two alternative methods. Either one will get you full marks in the exam if that came up. So there is now a group problem solving question beginning on slide 64. If you have a go at that, pause the video, have a go at that, and then I'll come back and show you how to solve it. Okay, so this isn't the easiest diagram to reproduce, again, because it's 3D. Hopefully you'll understand what's happening. I'll try and talk you through it as we go. Very similar to the previous question. The biggest challenge here is identifying exactly what you're looking for and what's happening in the diagram. The only line I haven't labelled is line OA, so O to the point where the force is acting A. Now in your diagram it appears to be going along the same line as the force itself. if only that were true. But we'll work through, and hopefully that will become more apparent. So the first thing you would do is, how do you get from O to A? Define line ROA, the position vector. You can leave this as millimetres, or you can change it to metres. I'm going to change it to metres because that's what the notes do, and I'll stay consistent with the notes. So to get from O to A, you're going to have to go in the X direction 300 millimetres. I should use a different colour there. I'll use blue. So 300 millimetres, but you're also going to have to go slightly further. So if I draw it end on, this is looking at it from this perspective. So you're looking at that end. That's an eye, in case you're not sure. 300 millimetres is this bit that I've drawn in blue already. This is also 300. That is 30 degrees. So this distance here that you're interested in, will be 300 sine 30. I believe that's 150. So your ROA will be minus 450, minus because it's going backwards in the X direction, minus 450 I, or minus 0.45 for me, I, because I've put it into metres. In the J, it's simply going along 300 millimetres, so that's this bit here, nice and easy. So it's plus 0.3 J. And in the Z, the K direction, that's going to be this bit here, which equates on my other diagram to this bit here. So that should be 300 cos 30. 300 cos 30 is 0.26, and it's going upwards to get from O to A, so it's plus 0.26 K. I do Pythagoras on that, so 0.45 squared plus 0.3 squared plus 0.26 squared, all square rooted. ROA, the distance from O to A, comes out at 0.6 metres. I can then find a unit vector for OA, and that would be minus 0.45 over 0.6 I plus 0.3 over 0.6 J plus 0.26 over 0.6 K. So I've now found my position vector, the distance from O to A, and a unit vector. I also need my force, which I haven't actually labelled on here. It should be going that way, force, which is 300 newtons, but I haven't got space to write that on the diagram. But I need that in terms of I, J and K. Just skipping back slightly, the force is actually acting, as you look at the diagram, there are two panels from O to, if I start to annotate, so let me find a new colour, from O to there is in the XY plane, from here, so from here to here is in the XY plane, and from this point that we've just finished out up to point A of interest is in the X, the Y and the Z plane. So if you imagine that it was once touching the Z axis here, and the force was acting at 30 degrees from the Y axis, so imagine that used to be the Y axis, and it's then been folded back 30 degrees, so it's moved through 30 degrees to there. Okay, hopefully that explains a little bit more about which way the force is acting. There is a grey shaded triangle in the in slides 64, 5 and 6 that should help you to understand that slightly. But if we move on, I'll try and explain as we go through more how to find the force. You are going to need an F dash line as well. So your force as a vector is going to be, well, you're going to have an fx, an fy, an fz component, and I'm going to keep skipping back to the original diagram. So fx is going to be the component that is acting. You're first of all going to have to resolve it to act along. Let me find another colour. I don't know how many I have. Oh, that's lovely. You're going to have to resolve it to act along this line here. And we'll call that f dash. Once you've got f dash, you can then resolve it to fz and to fx. Fy will come straight out, because fy will be the purple line that's already shown. So let's do fy first, because fy will hopefully make more sense, and you might have to refer to the diagram in your notes. So fy will just simply be 300, because that's the force, cosine 30. F dash, which will take us to the brown line, will then be 300 sine 30. Fx will then be 300 sine 30, and then another sine 30. And Fz will be 300 sine 30 cosine 30. So hopefully that makes sense to you. You can then put those together. When you put those into calculator, you'll get minus 75i for your x component, plus 259.8j for your y component, plus 129.9k for your z component. If I square these three aspects and square root, the magnitude of that force will be 300 newtons. Now you already knew that because it was told you in the question. It is a good way to check that you've done everything right. It's a good logic check. So the final part of that, now you've got your force as a Cartesian vector, you've got a position vector for line OA, you can start to do a dot product. So my force dot ROA is going to be minus 75 times minus 0.45, so it's the I aspects multiplied together, plus 259.8 times 0.3 plus 129.9, apologies for that, 129.9 times 0.26. So my overall result there will be 145.5 Newton meters. I can then find my angle, theta, because I can say it's 145.5 divided by 300. So we've got the dot product on the top, we've got the force we were given, and we're going to times it by the distance, the r as a magnitude, length of line ROA if you like, and that will give us, no, that will give us nothing because I haven't put inverse cosine in. So that will give us 36.1 degrees. If you recall, there was then two ways you could solve this. So using that 36.1 degrees, we can say the magnitude of force OA is F cos theta, which is 300 cos 36.1, which is 242 newtons. The alternative way of solving it is, which I'll change to a different colour just so you know it's an alternative method. FOA is going to be the vectors, the dot product of the unit vector. So that will be minus 75 times 0.75, sorry, times minus 0.75, plus 259.8 times 0.5, plus 129.9 times 0.433, which will again equal 242 newtons. So that's giving you some idea of using the dot product in resolving forces, calculating how much of one force is acting along another line, and work through a couple of examples to do with that. And that concludes the videos for Lecture 2.